Hey everyone, welcome back, and today let's solve Leetcode problem 3337, titled Total Characters in String After Transformations Part 2, the counterpart or the second portion of the problem that we solved yesterday. So we're given a string S consisting of lowercase English letters, an integer t representing the number of transformations to perform, and an array nums of size 26. And in one transformation, every character in S is replaced according to the following rules. We replace S at index I with the next nums at S at I minus a consecutive characters in the alphabet. So, for example, if S at I was equal to the character A, and nums at index 0 was equal to 3, well then the character A would then transform into the next 3 consecutive characters ahead of it. So it'd go from A to B, C, D. B, C, D are the next 3 consecutive characters in the English alphabet after A, and so it transforms or results in B, C, D. The transformation wraps around the alphabet if it exceeds z, much like how we saw in the last problem as well. In this case, the way it works, or the way it's structured, is, for example, if s at I is equal to y, and nums at 24, that's the, again, index of y in the alphabet, if that's equal to 3, well, then we know that the character y is going to represent, or rather, transform into the next 3 consecutive characters, which would be the z, that's followed by the y, and then wrapping around the a and b, which are the other 2 next consecutive characters after the z, because z wraps back around to ab. Right? That's why we have ZAB when nums at 24 is equal to 3 for y. Now we want to return the length of the resulting string after exactly t transformations, and since that answer may be very large, again similar to yesterday's problem, we want to return it modulo or modded by 10 to the 9th power plus 7. So in example 1, we have our input array s, or rather input string s, to be abcyy. T is equal to 2, and what t equals 2 signifies is that we have to actually apply or perform 2 operations as a whole on the input string s according to those following rules. And in this case, again, we see that their input array nums is that guaranteed size of 26. Right? That's basically just telling us, again, how many consecutive characters that we have to wrap around or flip or transform each character for, with every index being mapped to its kind of position in the English alphabet. So A would be mapped to index 0, this is for B, this is C, and so on and so forth, and this 2 is going to be corresponded to Z. Right? That basically says for any Z, we have to transform it to the next 2 characters, which in this case would wrap around to AB. Now, once we actually apply all those 2 transformations to the input string s, we see that our final resulting would become CDEA BAB. Right? Let's go ahead and look at why exactly that is. In the first transformation, we see that all A, B, and C, they all are simply just transformed to the next character consecutive to them because they're all being mapped to a 1, and so that would become B, C, and D for A, B, and C correspondingly. For y, however, still the same logic, we still have to wrap it around only one time because nums at index 24 is still just equal to 1. But in this case, those 2 y's will then become 2 z's because they go to the next character. So become B, C, D, Z, Z, right? That would be the resulting string after the first transformation. And if we apply the second operation, second transformation, that is, when t is equal to 2, we see that B would then be equal to C would then become D, D would then become E, but then those 2 z's that we actually got after the second transformation, they would wrap around, in this case, to the next 2 characters, because we see nums at index 25, it's actually 2, meaning any z would go to AB, and so those 2 z's would become AB, AB, hence why we have CDE AB. Right? That has a resulting final length of 7 characters, hence why 7 is our output for the context of this problem. Now to quickly gloss over example 2, a very similar logic here, except our input string s is azbk. We only have 1 transformation to make, and every single character, regardless of its index, of course, as you can very palpably see, is going to be wrapped around or transformed 2 times to the next 2 consecutive characters, and so it would become azbk, doubling its length, of course, because each value is 2, and we only have 1 transformation, to a value of 8, right? A would become bc, z would become ab, and so on and so forth to get a final resulting string of bc, ab, CD, LM, right? So for the constraints here, we see that the length of our input string s is going to be between 1 and 10 to the 5th power. S is only going to consist of lowercase English letters. Our t value, or the number of transformations that we make, is going to be between 1 and 10 to the 9th power. The length of our input array nums, as the problem kind of confirms here, is always going to be 26 for all the 26 letters in the English alphabet. And nums at index I is always going to be between 1 and 25. So really, that we don't have to worry about, having too many next consecutive characters that are greater than the number of characters or the number of letters that we even have in the English alphabet, to avoid any weird and complicated edge cases like that, right? So before we actually get into the main observations here, let me just fix my microphone really quickly. All right, so kind of how are we going to solve this problem on a high level, looking at how this problem is structured and all the different parameters that we're going to have. There's actually something called matrix exponentiation, right? Basically, the way that's going to work is we're going to model that transformation, or model all the different transformations that we have to make based on our input array nums as a matrix, right? Again, the matrix is nothing but a two-dimensional array that has both rows and columns. It's very similar basically just to a grid, right? And for the dimensions of that matrix, or it's going to be of course 26 by 26, right? Because their input array nums is also going to be of length 26 for all the 26 characters in the English alphabet, right? Our matrix, we can just call it T or M, doesn't really matter. T, if you will, at index I, index J, would represent the number of times that character, the string A plus I, transforms into the character A, the character A plus J in one transformation, right? Basically, again, the number of times character A plus I transforms into A plus J for every index I comma J in the matrix that we instantiate, if you will, right? And to actually exponentiate that matrix, we're going to compute T to the power of T, where again, T is nothing but the input array that we have, or rather the input integer that we have that tells us how many observations, that tells us how many transformations that we have to make. We're going to compute T to the power of T, right? That's the matrix T itself raised to the power of T, where the matrix T is going to be the matrix name itself, and T is going to be the number of transformations that we have as our input, right? And that's going to actually model the transformation that we have after all T steps, or after all T transformations. And to actually apply the transformation, kind of simulating that, if you will, we're going to first count the initial frequency of each character in our input string S. That's kind of like our base case, like we saw with yesterday's problem, before we even started applying any transformations, and then multiply that frequency vector with the matrix, capital T to the power of T, right? That's kind of how I'll refer to it. Capital T is the matrix name, and lowercase t is the actual input integer number of transformations, right? We're going to multiply that frequency vector with the matrix T to the power T. That's actually get the final frequency of each character after all T transformations. And then to finally calculate the total length, again, very similar to yesterday's problem structure, we sum up all the values in the final frequency vector to get the total length of the resulting string, basically, again, the number of total characters that we have after all T transformations are completed. So the code is actually rather hefty here. It's a lot of lines of code, so we'll kind of break it into different chunks here because we're going to have many different helper methods to help solve this problem for the different observations and matrix kind of operations that we need to configure, right? So the first thing, before we even get into any helper functions, if you will, the first thing that we're going to do is actually initialize our mod constant, right? That's exactly why, or that's what the problem told us to. It's to prevent integer overflow. I'm just going to call it mod, and the way it's going to be initialized is going to be 10 to the 9th power plus 7, right? Again, the whole point of mod is to do nothing but avoid integer overflow. As we saw per the problem statement here, we want to return our answer because it's very large by modulo, or rather modded by 10 to the 9th power plus 7. Now, as we see here, we have a def length after transformations method that Leetcode provides, just for us directly, immediately before we even start coding anything up. Now, in this helper function here, I'm going to initialize my own helper function here. I'm going to call it the get transformation matrix. And as the name suggests, it's going to do exactly that. Of the helper method, sorry. Right? So I'll, kind of quickly code out this helper method here and kind of explain how this actually works and the different observations and the different operations that the point of this matrix does, right? So in this case, we're going to only have one parameter here. It's going to be an input array nums. And the way it's going to work is we're going to initialize T. Again, T is going to be nothing but the actual matrix itself, and again, it's going to be two-dimensional. We can use something called list comprehension in Python to initialize or instantiate two-dimensional Python grids, or two-dimensional matrices, as we see for this matrix T. It's going to be 0 times 26, that's the number of rows, for, or rather, we can have an underscore as a filler iterator in the range of 26, right? It's going to be, again, a 26 by 26 matrix for the dimension, 26 rows and 26 columns for all 26 possible character orientations in the English alphabet, right? Now, let's actually start iterating over all the different indices in the range of 26. So for I in 26, basically, again, just 26 iterations here. And then that should be a colon rather than semicolon, and for I in the range of 26, we're going to go for every single possible step or transformation, if you will, in the range from 1 to nums at I plus 1. And for every step in this range, we're going to get T at I, and I'll quickly calculate this real quickly. T at I in this case, is going to be I plus the step value. And that's then going to be modded by 26. And finally, we're going to add 1 to that key value, or rather that index, if you will, and then return t after all both the external and internal loop kind of finish executing, right? So what are we really doing here? Basically, we know that each character can transform into multiple characters, and we know that's going to be based on our input array nums, right? Again, we know that for every index in the range from 26, our input array nums tells us how many next consecutive characters every single English letter in the alphabet transforms into. And that's going to be determined by their index or positioning in the English alphabet, where A would be mapped to that number of next consecutive characters, B always gets transformed into that many consecutive characters, and so on and so forth for all English alphabet characters in the range from, again, 0 to 26. As that's purely determined by our input array nums, right? That's the whole point of our input array nums, right? And so we have to build our transformation T, or rather transformation matrix T, accordingly to account for that kind of character offsets and transformation offsets when we encounter those different letters to be able to transform them in all T transformations, right? Now, we're going to have another helper function here. I'm going to call it matrix multiply, which is matrix mult, to account for the frequencies of all the different, operations that we're going to have. And in this case, it's going to take in 2 parameters. It's going to take in a parameter A and a parameter B. I'll just capitalize them just to make them a little easier to see. And we're going to output a list, right, with integers, of course. Now, in this matrix multiplier, or just matrix multiplication function here, I'm going to initialize a result. And again, we're going to be using that 2-dimensional list comprehension here that we saw in Python when we instantiated the matrix T on line 5, right? So it's going to be initialized initially to all zeros for all the cells, times 26 for the number of rows, just in the range of 26, right? Again, because the dimensions of this matrix, or the result grid, is going to be 26 by 26, hence we have 26 rows and 26 columns, hence why we have multiplication times 26 for every single index in the range of 26 to get those dimensions accordingly and instantiate a result accordingly, right? So now, let me just quickly code it up. For I in the range of 26, again, still for all the English alphabet indices, for every j, for I, every I in the range, again, still of 26 here, and we're actually going to have a third inner loop here. This is going to be for, for k in the range of 26. We're going to then get the result at still I comma j, right, where I comma j is nothing but our cell value or our indexing, if you will. And the way this is going to be computed, a little hefty here, it's going to be result at index I, index j. And from this, we add onto it our A at index I, index k, where A is nothing but, another matrix by itself, hence why we have 2 indices for that as well. And that's going to then be multiplied by B at index k, index j. And of course, we don't want to forget to avoid integer overflow, and the way we're going to do that is mod that result value by mod and effectively return the result. Right, so how does this really work here with these 3 nested loops, actually? Effectively, we know that matrix multiplication, we need to do it for combining those different transformations across all the different frequencies of elements that we actually transform in each transformation. And so we define this matrix multiplication function to help actually multiply 2 matrices under that modulo operation, right, to account, again, for that integer overflow. Now, for the final method of this solution here, that's going to be matrix power, or just matrix pow, if you will. I think it's a little easier to type out. And in this case, we're going to have 2 different parameters. It's going to be, of course, matrix itself and power as our 2 parameters, right? Now, in this kind of result, or in this matrix power helper method here, again, we're still going to first initialize a result. And the way this is going to be structured is going to be the integer if I is equal to j, where again, I and j are nothing but iterators, for every j in the range of 26. And again, still using nested loops here, sorry about that. Alright, I should actually be for every j in the range of 26. For every I in the range of 26. Right? Now, once we actually instantiate or initialize this result here, now, while our power is non-null, meaning while we still actually do have a valid power here, we know if the current power value, that is, if we mod it by 2, if that actually has a non-valid output, or rather, if that is actually non-zero, meaning it's not divisible by 2, it's still an odd power here, we're then going to get the result. So while that's still not an even power that's divisible by 2, or rather modulo by 2, yeah, it's divisible by 2 equally, we're going to get the result is going to be matrix mult. Again, we're just calling that helper function matrix mult, and in this case, the two matrices that we're actually multiplying would be our current result, and it'd be the current matrix itself. Right? If the power is actually 2, and while the power is still non-null, we're going to get the matrix itself and increment or update that. And the way it's going to be called, again, is going to be matrix, still using matrix mult as our helper function here, and in this case, the two parameters are going to be matrix and matrix both times, and finally, once we initialize matrix to that new value, we then actually get the power and divide it by 2, right? Because that's one more operation that we've had on the power, now we have to divide it by 2. And effectively, we then return the result, whatever that matrix would be after this transformation, right? So effectively, we're using that binary exponentiation to efficiently actually compute t to the power of t. Again, t is our matrix that we instantiated or initialized in def get transformation matrix, and we simply just calculate or compute that matrix t to the power of the number of transformations t using the matrix multiplication frequency indices, using our matrix mult helper function here in the matrix power helper method, right? That's the main kind of use case of this matrix multiplication method, right? Now, that's going to be kind of it for the helper function here. Now, the next step that we have to actually do in our solution is actually to build that transformation matrix and raise that to the power of t using our helper methods and getting that as our final output after we fully perform all t transformations on our input array nums, or rather on our input string s, right? So again, I'm going to get a new t here. That's going to be get transformations. That's the whole point of these helper methods here. Get transformation matrix. And our input array A, and our input array parameter is going to be nothing but our input array nums, right? That's the whole point of the parameter here. It's going to be nothing but nums. So we're going to pass in nums as our parameter for get transformation matrix helper method. All right, and now we'll get t power, again, still using the helper method here, but in this case, it's going to be matrix power. And in this case, for our parameter, it's going to be t and t. Why? Because, of course, we're actually raising to the power of the matrix t itself to the t times, or to the power of t, for where t is our transformation. We're building that transformation matrix, and we're raising it to the power of t, and calling that value t power, right? And here we have to actually calculate the frequency of each character in the original string before actually applying any operations here, before we actually use our helper methods to actually apply those, simulate applying those operations to the frequency of different characters in our input array string. And so the way we do that and actually calculate the frequency before we actually apply any operations or transformations is basically just, again, very similar to yesterday's problem here. Initialize a count of initially all zeros for frequencies times 26 for the dimensions of the count, because we have 26 in English letter alphabet characters, and for every C or character in the input array S, we're going to get count, and again, the way we actually calculate that is the ord of A minus, in fact, a simpler way to do that would be the ord of C, actually. Ord of the current character C minus ord of A, and for that key, we're going to add on to it by 1. And effectively, that's going to be our count, right? Again, it's going to be the frequency of each character in the original string mapped to its frequency, right? Meaning how many times it actually appears in the input array, right? Again, for every index, that's basically the position of each character in the English alphabet. That's going to be representing at that index the number of times it appears in the input array string initially or originally before applying any transformations. That's the key part. Now we have to actually, multiply those initial frequencies with the transformation matrix to actually get that final resulting output, and simulate applying all those t transformations to our input string s, right? Using again those matrices. So the way we would do that is actually initialize the result to be 0, and this result is actually going to finally store the number, or rather total number of characters, or the total length of the final resulting string of our input string s after all t transformations, and this is effectively what we're going to return as a result. And the way we actually compute this and kind of update this is for every I, again, in the range of 26, for every j, you go through all the pairs in the range of 26 for all the different cell values in our matrix, we're going to get the result, and it's going to be computed by result plus, in fact, let me put this in parentheses first. It's going to be result plus count at I, whatever our current value in our outer iterator is at I. That's going to be multiplied. By t power at I comma j, or rather I index ij. And then finally, that's going to be modded by, of course, our mod value to again still continue preventing integer overflow. Right? So it's going to be result, whatever result is at the current iteration, plus count at index I. Where again, count is the initial frequency of whatever character that is we're at right now, times t power at index ij, where t power is again the result where we actually raise a power t to the power of t, right? Raise the initial matrix t to the power of t, t times, right? To actually get that matrix power helper method, right? And we're going to be multiplying that with result plus the initial frequency of that character, and of course modding that by mod, and effectively returning our result to finally eventually store the resulting output to be the number, rather the resulting length of the resulting string after all the t transformations, basically the sum of all of the different characters with their corresponding frequencies after we apply all t transformations, right? We're going to multiply, again, on a high level, just the initial frequencies with the transformation matrix to get the final count, and then sum them up to get the total length that's stored in the result integer, right? So unless I made any syntax errors here, this should be accepted, this should be a valid solution. Okay, let's go ahead and check what I did wrong here. First step in the yeah, that should be a comma. Sorry about that, not a period. So it works now. Let me kind of just zoom out here so you guys can see this a little better. And as you can see, this really is just about as efficient as you can get it to be, right? So this is kind of the code high level here. Let me kind of zoom out here just really quickly so you guys can get an entire snapshot of how this really looks. Right, and as you can see, it is just about as efficient as you can get it to be, right? So on a high level, how are we really solving this problem? What is kind of the process behind it? Effectively, we're combining string manipulation with matrix exponentiation. We're modeling the transformations that we have to apply, all t of them, to our input string s as matrix operations, and then we just efficiently compute the result, even for larger values of t, kind of showing, again, how we actually use mathematical concepts to these Leetcode problems, where we can use matrices to keep track of the frequencies of all the different characters, I comma j, for those transformations in the entire input string s, to model how they'd actually pan out after all t transformations, and increment our result accordingly to store the total number of characters, or the resulting sum of all the different characters after t transformations in the input string s, right? So for the runtime complexity here, to actually build our transformation matrix, we know that that's going to be big O of 26 times the maximum of nums at index I, and really because constants and coefficients don't really matter in runtime complexities, on average that's simplified down to big O of 1 for that specific operation. And for our matrix exponentiation, this is the pretty slow part here, this is going to be big O of log t times 26 cubed, right? Because of course we have 3 nested loops all in the range of 26, and in this case that's going to just really be big O of log t, right? Because again 26 cubed, it really just simplifies to big O of 1, again because coefficients and constants don't matter in complexities, and so this matrix exponentiation part of the runtime complexity is going to be big O of log t. And for the final computation here, we see these final nested loops here, both in the range of 26. That's going to be big O of 26 squared. Again, doesn't really affect our runtime complexity because it's really just constants regardless of how large our input size is. We're always going to be iterating over 26, and so that's not going to affect our runtime complexity either. That's just an operation of, on average, big O of 1, and so the overall runtime complexity is big O of log t. Now for the memory or space complexity here, to actually transform the matrix and its corresponding powers, that's again big O of 26 squared, like we saw with those 2 nested loops here. And rather that we saw with the 2 nested loops here. And so because of that reason, it's still going to be big O of 26 squared, or big O of 1 for that operation. And for our actual frequency arrays, again, the frequency array that we see, as you can see in count, that's actually going to be big O of 26 regardless of how large our input size is, because we're guaranteed to only have 26 unique characters in our input array, because there only are 26 distinct characters or alphabets, or rather characters, if you will, in the English alphabet, and so that's going to be also big O of 1, and so the overall memory or space complexity is also going to be constant, or big O of 1, right? So basically, you know, even though we have a lot of different nested loops here, with a lot of different nested loops. We know since our constants are small, because the alphabet size is always going to be fixed or capped at 26, regardless of how large our input is. It's still going to have our solution is still going to be efficient because we're always mainly iterating through 26, which is still a constant runtime, right? So that's going to be it for today's video. If you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.